This is the central portion of the alpha apparatus spinning into view. You're looking at the silicon annihilation detector, which is the 3 layers of segmented things. They'll peel back in a second so you can see what's inside. The tube sticking out either end is the inner portion of the cryostat, the liquid helium vessel for the magnets. Now you see the superconducting magnets that make up the atom trap. There are an octopole and 2 mirror coils. These are what actually trap the antihydrogen atoms when they're produced. They produce very strong magnetic fields that grow from the center of the apparatus. The arrows indicate the direction of the current in the superconducting magnet coils. It's about 1,000 amperes for the octopole and about 700 in each mirror coil. Now those will peel back. You'll see the vacuum chamber open up. The yellow cylinders are the electrodes for the penning trap. These are used to help trap the charged particles. The whole device sits in a superconducting magnet that gives a constant field of about 1 Tesla and holds the particles transversely to the axis. These are the potentials in red applied by the electrodes. You see a cloud of positrons in green in the center and a cloud of antiprotons that's being driven into the positron cloud to form the antihydrogen. These particles obviously have opposite charges, so they're in different curvature potentials. So now the antiprotons go into the positron cloud, hopefully very slowly so that you can make cold antihydrogen. 2 positrons scatter in the field of the antiproton and produce the antihydrogen atom. So that's it, antihydrogen, 1 antiproton with a negative charge, 1 anti-electron or positron with a positive charge. So if that antihydrogen is formed and it's slow enough, it will stay in this magnetic bathtub. You can see it at the bottom. This is the potential that's used to hold the antihydrogen atom. So if it's less than 0.5 Kelvin above absolute zero, it'll stay there. Then if we want to see if it was there, we release it quickly. That's what's happened here. We've turned off the magnets. The antiproton from the antihydrogen annihilates, produces high energy charged particles which come out and are registered by the silicon detector. So we can recreate the position at which the thing annihilated. That's how you know you had antihydrogen. Now here's the experiment we've just done. The antihydrogen is trapped because it's slightly magnetic, and that's indicated by the little arrow flying around with the atom. We shine microwaves on that little magnet and cause it to flip into the other direction. It'll happen more slowly here. You see the magnetic moment, sort of like a compass needle in the antihydrogen atom, has to point in one direction for it to be trapped. The microwave radiation flips that magnetic direction, and that means that the atom is untrapped and comes out. And that's what happens. You detect the annihilation. You need to have the frequencies of the microwaves exactly correct. And that's what's resonant about this experiment. So if you tune it correctly, you force the antihydrogen to come out, and you can detect it. That's how you know you've done a resonant interaction.